Hello, and welcome to our course Introduction to Data Analytics. In this lecture, we continue our work in descriptive statistics. To give you a timeline of where we are, we have discussed within descriptive statistics the various graphical and visualization techniques. And the second half of the descriptive statistics deals with summary statistics, the use of numbers to describe and summarize data. Within summary statistics, in our previous lecture, we spoke about measures of central tendency. In this lecture, we will be concluding the use of summary statistics with discussion on measures of dispersion. So we should be at this point fairly familiar with the use of this data set. Essentially, the data set is just a sample which talks about different data points over a certain range, and the histogram that you see to the right hand side of this is a histogram that is generated from this data set. So we covered histograms during our lecture on graphical techniques, and we've used them extensively in our discussions of measures of central tendency. Again, to be very clear, measures of central tendency and measures of dispersion and the specific metrics that we've discussed in them. So for instance, in measures of central tendency, we spoke about mean, median, mode, and today we're going to be speaking about some metrics associated with dispersion. All of these metrics don't in any way, shape or form need this histogram, right? They directly operate on this data set. And in some sense you might say, so why even talk about this histogram? The idea is that you're absolutely right, we don't need this histogram, but it really helps to explain the concepts, and it's also a healthy way to start thinking about these metrics and start thinking about these distributions. It will help us also in the long run when we cover concepts in probability distributions. So now, having said that, let's talk about what measures of dispersion seek to capture. We spoke about in the last lecture how measures of central tendency try to capture, in some sense, a central value, right? Some central value within this range of values that this data set takes up. So the range of values that this data set takes up is shown here. And in some sense, the histogram captures their likelihood in this axis. So the range is here on the x-axis, and the y-axis is in some sense the likelihood of seeing that data. And we spoke about how measures of central tendency try to capture what appears to be like a central value, and we spoke about different metrics that do that. Measures of dispersion talk really about how the data is dispersed around this value. How does the data deviate from this value? For instance, if every single data point, and let's for now assume that 10 is our measure of central tendency, one measure of central tendency is the mean, so for now let's just say we're using the mean. So if 10 is the mean, then if every single data point in this data set was equal to 10, and it's not what is here, but it's every value is equal to 10, then there would be no deviation of data from 10. You would just see a single tall line in this histogram, and none of the sides, none of these would exist altogether. But that's not the case, right? Typically, most data sets, the values are going to be different, and you might have some measure of central tendency, but there's going to be some amount of deviation of the data points on either side to this central value. Now, measures of dispersion try to capture that. Do the values deviate a lot from the center, or do they deviate very little from this center? And that's what measures of dispersion seek to capture. To understand the different measures of dispersion, let's go back to the data set that we were using when we were speaking about measures of central tendency. So I've used the same data set out here, and the simplest measure of dispersion is range, and a range is quite simply nothing but the highest value minus the lowest value. So in this particular case, the highest value is 9, the lowest value is 1, so quite simply 9 minus 1 is 8. And that should be intuitive for you. Given that the mean of this data set is about 4.5, 4.6, a measure of dispersion is just the max minus min. Now, if, for instance, if there was very low dispersion, then the highest value would be close to 4.6. The lowest value would be close to 4.6, and so that range between max minus min could have been smaller. At the same time, if this dispersion is very high, on the high side and the low side, your max and min values are going to deviate a lot from the 4.6, and so you'd have high dispersion. Okay, so that's a simple one. The second one is the interquartile range. And the idea here is it's highly related to the concept of median, where you would arrange the data points and you would kind of take a central data point. Another way of saying that we discussed that procedure of median during measures of central tendency, but another way of thinking of it is that you're taking the 50th percentile point. With the interquartile range, what you're doing is you're taking the 75th percentile point, or the third quartile, and subtracting from it the 25th percentile point. The idea being that within this data set, if there's a high level of dispersion, then the range between the 75th percentile point to the 25th percentile point would also be high. And if the dispersion was low, then this range would be low. And it's really noteworthy that this is the concept that gets captured in box plots, which we discussed in the graphical techniques. We spoke about how in the box plots the upper line of the box plot and the lower line of the box plot correspond usually to the third quartile and the first quartile of your data set. So and this is also known as the interquartile range. So it might be abbreviated to IQR in some textbooks, but this is also a measure of dispersion. We then come to what is a fairly popular measure of dispersion. And the idea behind this is to essentially look at how much each data point deviates from the mean that you've just calculated. So xi represents each data point because I goes from the first value to the nth value, and in our particular example n is 12. And so we want to take each data point, see how much it deviates from the mean. In our particular case for this data set, the mean is 4.58. So we will take the first data point, which is 3. So the data point 3, and we'd subtract that from 4.58 and square that value. We would take the second data point, do the same thing, and we would keep adding up these squares. And once you add up these squares, you take something that kind of looks like an average. And it's not an exact average because you have this -1, and we'll talk about that in a minute. But in concept, you essentially are trying to get an average of the squared deviation, and you'll ultimately take a square root of this. Now, when you take the square root, what you get is the standard deviation, and when you don't take a square root, you get this measure called variance, and variance is also a measure of dispersion. And in concept, the only difference between standard deviation and variance is that one is the square root of the other. Again, now that you understand how a standard deviation is calculated, let's go through some questions that might have come up when we discuss standard deviations, given that the other two methods that we've discussed are fairly straightforward and clear. So here are some questions that always go with standard deviation. Why do we use the square function on the deviations, and what are its implications? So what we're referring to here is the fact that we actually take the square of the deviation. So what's the purpose? If you want to calculate, if you want to get some measure of average deviation, why not just take the deviation and take the average of it? And the answer is fairly straightforward to that. The answer is that just by definition, because you're looking at the deviation from the mean, there are going to be some points that deviate from the mean on the positive side, and there are going to be some points that deviate from the mean on the negative side, right? So 3 minus 4.58 would lead to a negative number, whereas a 9 minus 4.58 would have been a positive number. And again, by definition, because of how you calculate a mean, and the math for this is fairly straightforward, you will find that if you just took the deviations, some positive numbers and some negative numbers, and you added them up, you would always get 0. And that's because of how the mean is calculated, because the mean is nothing but the sum of all the numbers divided by the total number of such numbers. So by definition, just taking the deviation would result in some positive numbers and some negative numbers, which would cancel each other out and give you 0. So what you're really trying to capture is an average deviation, but you don't want the signs. So what's one great thing you can do is to square it all, right? So when you square a number, whether it's negative or positive, you always get a positive number. And the other really interesting thing is, the only thing that matters is the magnitude. So minus 3 square is 9, which is also the same as plus 3 square. So the idea is that the square function is symmetric on the plus minus side, and it always gives you a positive number. So for that reason, we use the square function. Now, are there some implications of that? And the answer is yes, there are some implications. The implications is the effect that squaring has, right? So let's say you had two separate deviations of 1 unit each, right? So let's say you had two data points that signified that there was a deviation of 1 unit. So given the average is 4.58, let's say you had a 3.58 deviation. So 3.58, and you had another data point which was 5.58, right? So both of these would have a deviation of -1 and +1, and when you square these two numbers, right, so you square these two numbers, the answer comes out to be 2. Okay, so that's what happens when you do this entire squaring process. Now, what happens when in one case, so we had two, we just focused on 2 data points, right? Now what happens in one case when you just, in one case you're right on the mean? Okay, so you're right on the mean. In the other case, you're deviating by 2 points essentially, or whatever the unit you're using, your deviation is 2 units, right? Okay, so here the deviation, because you're comparing it to the mean, you're essentially just replacing this you're replacing this 3 with this 4.58, and we're looking at what would happen. Okay, so because you're doing that, your deviation is 0. Okay, here your deviation is 2, and because it gets squared, that becomes 4, right? And so your cumulative deviation in some sense is 4, whereas in the previous case your cumulative deviation was only calculated as 2. In both cases, you deviated by 2 units from your mean across the 2 data points. In one case, you deviated by 1 unit in the first data point and 1 unit in the second data point, but the sum of the squares led you to a number 2. Right? In the second case, you deviated from the mean by 0 data points in the first, by 0 units on the first data point, and again 2 units in the second data point. So in both cases, if you just look at the actual deviation from the mean, in both cases you had deviated by only 2 points. But in the second instance, in this instance, you would be recording a squared deviation of 4 units, which is twice as much as the squared deviation of the first case, which is 2 units. Now, many people like that, and there are many contexts where that makes a lot of sense. There are some contexts where this just does not make sense. But that's one of the implications of squaring the deviations. Okay, so the second question is, why do we work on standard deviation and not the variance? So the idea is, why do we take this square root? Why not just report the variance? Why do we, I mean, because they're both the same function. And the answer again is fairly straightforward. You have a data set in some units. This 3, 4, 3, 1 could have some units, and these units could be things like simple things like rupees or kilometers per hour, whatever it is that you might have been collecting data on. And when you report a deviation from the mean, the units would then be in squared if you're using variance. So if you use variance, you'll have to report a value that's in squares. And so what does it mean to say rupees squared? What does it mean to say your dispersion is 500 rupees squared? And rupees squared is not something that we can understand or fathom. It's far more intuitive, and it truly is far more meaningful to say your deviation is 23 rupees from the mean. You can make decisions based off of that, and you can gather some insights based off of that. So the third question, and often a very interesting question, is why do we average by dividing by n-1 and not n? So the idea here is that the sum of the deviations is always 0. And so the last deviation, right, because you are essentially doing a series of deviations. Now the last deviation you can be found once we know the other n-1 deviations. So we're not really averaging n unrelated numbers, you're really averaging only n-1 squared deviations. In some sense, it's almost like only the n-1 squared deviations can vary freely, and we average by dividing the total essentially by n-1. This is also the concept of degrees of freedom, which is how many of the values can actually move freely can move freely and still maintain the final statistic. And in this case, the final statistic is the mean, because you're subtracting each number from the sample mean. Now the important thing is, this mean, which is 4.58 in our case, is something that was calculated from this data. So from the same data which you're using to calculate the standard deviation, you calculated the mean, and that's the reason essentially that you're using the n-1. If instead you were not using this mean, but someone came and told you what the true mean of this data was, if someone said, here's a data set, oh, and by the way, the mean of this data set is 5. So they just told you the data set, or you knew the data set from past experience, or you were able to compute that. Then you would not have to do the n-1, and you would do the n. But also out here, you would not substitute 4.58, you would be substituting 5. So in each of these places, you would be substituting 5, which is the true mean. We call that the true mean, and we call 4.58 the sample mean, because 4.58 you calculated from this data, whereas 5 is something that you knew on principle, or you were able to use some other source to know what the true mean was. Now, another way that people like to describe this is also to say, for instance, that if this 3431, this data, is ultimately a sample from some other population, then you need to essentially do what we just discussed now, which is to use this n-1 and take the sample mean. So again, we're talking about the case where nobody comes and tells you what the true mean is. So your only hope is to calculate a mean from the data, and you've calculated 4.58. And because this data set is a sample from something else that's generating this data, the right way to do it is the way the standard deviation formula right now is shown. But if in some sense this data is the population, right? It's not a sample from some universe, but it's the real deal. Then again, the idea would be to use n and not n minus 1, because this is the true mean. And again, out here you would be substituting the 4.58, but then this would be called a population standard deviation. So it's POP, population standard deviation. But more often than not, in terms of the more realistic situations that you'll encounter in life, I think it's fairly safe to say that if you're taking the sample and you're calculating the mean, use n minus 1. If you are given a sample data set but you already know the mean, that is, you're not calculating it from this data set, you already know the true mean. In that case, you can just go ahead and use n instead of n minus 1, and that would be the right standard deviation. So that's as far as standard deviation goes. But before we conclude on measures of dispersion, it's worth mentioning that there are some other measures of dispersion out there, and these are called mean absolute deviation, and there are many variants to it. But the core idea is that with mean absolute deviations, you replace what you use in standard deviation, right, which is the deviation of each point from its mean and squaring it. You replace that with an actual deviation. So the deviation and this sign, which is the two vertical lines on either side, what they essentially mean is that that negative symbol just goes away. So a 3.58 minus 4.58, which would result in a minus 1, would just be written down as a 1. And so would a 5.58 minus a 4.58. So negative signs are just taken off, and then you do, and the other operations are the same. The good thing with mean absolute deviation is that it has a lot of variance. So it's like, what is the average deviation from the mean? That's the typical case, and that's what I've written down here. But you can also replace this x bar with median of the x's. So the mean absolute deviation from the median is another case. And you also have cases like, what is the median absolute deviation from the mean, the median absolute deviation from the median. Obviously, our previous lecture on understanding the pros and cons of means and medians would play an important role in making such a selection. So that should conclude our lecture on measures of dispersion. In the next lecture, we will continue with descriptive statistics, but focusing more on distributions. Thank you.